Well, from the class today, hope you can recall that the definition of H, enthalpy, was internal energy plus pressure times volume. Therefore, if you want to get the difference between H and U, that is H minus U, you will see that it is equal to P times V. Here in the question says molar enthalpy and molar internal energy. Those are none other than enthalpy and internal energy per mole of a substance. So therefore, you can get the HM by taking the total H and divide by the mole of the substance. In other words, HM is basically equal to H divided by the M, mole of the substance, and UM, the molar internal energy, is U divided by the mole of the substance. So again, molar enthalpy of the substance is just the total H divided by the mole of the substance, and the molar internal energy of the substance is the total internal energy divided by the mole of the substance. So then to get HM minus UM, you just need to take this equation and divide it by the mole on both sides. And then you get basically P times V divided by mole. The same mole that you divide here is what will be happening on the right side of this equation as well. So now you can see that in order to answer our question, what is HM minus UM of liquid water at 1 bar and 298 degree Kelvin, you just need to know two things. One is the pressure of the liquid water and this volume per mole of liquid water. And the volume per mole is basically molar volume, right? Molar volume. So, and as you can see in the question, the pressure is already given as 1 bar. So this is our P. So what we are left to do is to figure out the molar volume of liquid water. How do we do that? Maybe we can pause here one more time and think about it on our own. Okay, what did you get? What do you think? How do you get the molar volume? Well, molar volume is basically volume per mole, right? And that is basically the inverse of mole per volume. And mole per volume is basically a molar density, right? Here, we don't have molar density, but we got a mass density, 0.997 gram per cubic centimeter. And so then you just need to think about, okay, how do I convert a mass density that is in gram per cubic centimeter to something that is molar density, like mole per cubic centimeter, for example. And then you can see, okay, I need to convert gram per mole. What is the number you need in order to convert gram of a substance to mole of a substance? Well, yeah, it's a molecular weight. If you take this gram per cubic centimeter and divide it by the gram per mole, which is the molecular weight, basically you would get what? Mole per cubic centimeter, which is this molar density. In other words, from here, what we are saying is that you can get the mole per cubic centimeter molar density by taking the mass density rho and divide it by the molecular weight. In other words, if we go back here and think about what is a molar volume, then basically what you can do is you can take the inverse of this molar density and then put it over here, because molar volume was inverse of molar density, right? So then basically what we are saying is that molar volume can be obtained by taking the molecular weight of the substance and divide it by the mass density. Again, molecular weight is gram per mole. You should never forget that. And rho is usually in here, as in here, it's gram per volume, gram per cubic centimeter. Therefore, if you plug in those numbers, the unit you will end up having is what? Cubic centimeter per mole, which is molar volume. And the number, so okay, we got that. Okay, so now let's go back to our main focus over here, which is HM minus UM. HM minus UM is P times molar volume, and P was 1 bar, so 1 bar is equal to 10 to 5 Pascal. This is basically 1 bar, or let's retain the significant figure, 1.00 bar. 1.00, 10 to 5 Pascal. And then times molar volume, but molar volume can be obtained again by the molecular weight, 0. And then water's molecular weight is 18.1015 gram per mole. And then we divide it by the molecular weight, just like what we just said over here. So molecular weight is I'm sorry, not that. Okay, that's been a long day. Anyway, okay, so actually I need to take this in, right? The molecular weight, this is what we need to do here, is for the molar volume, you have to get the molecular weight and divide it by the mass density. So that's what we are doing. So molecular weight, 18 point something gram per mole. Mass density, 0.997 gram per cubic centimeter. And again, this unit gives you the cubic centimeter per mole. But since, if you actually now take a look at Pascal, Pascal is Newton per square meter, but then it's also, since you can multiply meter on both numerator and denominator, and then Newton times meter is equal to joule, Pascal is basically equal to joule per cubic meter. So we have got the meter here, but we have the centimeter here, so we gotta convert one to the other. So let me take the centimeter cube and work it out to convert it to meter cube. How do we do that? Again, you take the centi, the prefix as a number, and then it's centimeter, and then cubic centimeter means that the whole thing is raised to the power of 3. So then that means when you take everything out of the parentheses, it's 10 to minus 6 meter cube. So 1 cubic meter is equal to 10 to minus 6. I'm sorry, 1 cubic centimeter is equal to 10 to minus 6 cubic meter. So the whole unit out of this operation is now equal to 10 to minus 6 cubic meter divided by the mole, is basically what we got. Okay, so then here you can rewrite this. So you can see, okay, the operation basically boils down to 1 times 10 to 5 Pascal times 18.015 divided by 0.997 and then multiply by 10 to minus 6. And then the unit is that, sorry, it's somehow written in different lines, but this guy, cubic meter cancel out, and you will be left with just the joule per mole unit. The thing is, before you punch in the calculator, you can recognize that this one and this one can be worked out even before you put it into calculator. 10 to 5 times 10 to minus 6 is equal to 10 to minus 1, right? So that's 10 to minus 1. And then the other numbers are just 18 times 0, not 18, 18.015 divided by 0.997. So that's it. So if you plug in these things into the calculator, you get a number slightly more than 1.8015, and it ends up being 1.81, and then joule per mole. Okay, actually here, let me just summarize the key points. The key points, not key, the key points. First and foremost, in order to solve this problem, you need to know the definition of enthalpy, which is H equals U minus PV, U plus PV. Therefore, you should be able to deduce that or derive that H minus U is equal to PV. Second, you need to know what molar enthalpy, molar internal energy, and so on is about. It's basically total divided by the mole. Also, you need to know about the fact that the molar volume is none other than the inverse of molar density. Yeah, molar volume is basically how many volume units, like cubic meters, you got per mole, and then molar density is how many moles you got per cubic meter per volume. So it's just inverse relationship. So if you can see the connection between these two, and if you know how to convert mass to mole, then the rest calculation is pretty straightforward. The third key point is actually the meaning of the outcome of this calculation. Basically, what we calculated is the difference between the enthalpy and entropy of liquid water, right? And the answer ends up being something that's not even 2 joule per mole. And this 1 point something joule per mole is a very small number compared to, this is a small number compared with HM and UM. In other words, the difference between these two quantities for liquid water is not that much. This usually is in the order of kilojoule per mole, and that's what I'm saying. In compared to something kilojoule per mole, 1.81 joule per mole is small. So what does that mean? That means it's convenient. In biology, most of the systems work in liquid. And as you know, as we talked about in the class, enthalpy is easier to measure than internal energy. But since H is almost equal to U in liquid system, due to, and why is that? You can see it's because the Vm of liquid is really, really small compared with Vm of gas. That's the primary reason why the difference between H and U in the liquid is small. And because of that, in biology, if you can measure and deal with enthalpy, you basically can have a good approximation for the internal energy. So that is the significance of this fact.